Okay? During the discussion section this morning, some questions and comments arose about a quite interesting topic, about the question of the nature of the triggering and the stimulus requirement, the input requirement for acquisition of language, which bears directly on this so-called innateness hypothesis, which, as I tried to make clear, is not a hypothesis, but just a truism. The question is what form it takes. One case came up, I mentioned one case, which is the extreme case of language acquisition in the case of no input at all, zero input. That's, of course, the extreme. However, what was required was social interaction. That was necessary. That's apparently true for other kinds of development as well. So institutionalized children may be fed perfectly well, but they may not grow properly, just because of the lack of proper social interaction, whatever that's supposed to be. And it's been even shown experimentally with animals. So if lambs are taken away from their mothers, let's say, they can get the same regular nutrition, but they don't develop properly. There's some kind of, somehow the effect of social interaction seems to be a trigger, at least for mammals, for getting things going. And the interaction among these three children was apparently sufficient to get the language faculty to develop on the basis of no input, but with full perceptual capacities. Afterwards, some of us were talking, and there's another case in which the perceptual capacities as well are radically impaired. This is an interesting case. Actually, it's one that was studied by my wife. In the era when people used to get spinal meningitis, which is fortunately overcome, this disease in early childhood, which is completely debilitating, there were fair number of children who were deaf and blind from very early ages. And it turned out that a number of them were able to learn language fully, pretty fully. I mean, it turned out by a technique called tadoma, which involved placing the person's hand on the face of the person speaking to them. So you put your hand on the face kind of like this, and one finger gets some information from the vibrating vocal tracts, and other fingers get information from the lip movements, and that's it. That's the total information that they get, which is just, a ridiculously limited amount of information. Try putting your hand on your face if you want to see how limited it is. And on the basis of that input, with training, of course, there's a group of people who manage to attain what is so close, it's so close to full linguistic capacity that you have to carry out tests. You have to investigate exotic constructions to begin to find places where their knowledge breaks down. In a normal interchange, you wouldn't find any cases where it breaks down. There was a project on this at MIT in the electronics lab where they were working on sensory aids for people with various sensory deficiencies. And one of the subjects in this experiment investigation was a man who lived in, I think, in Iowa, a couple of 1,500 miles away, where he lived alone with his wife, who was also deaf-blind and had learned the same technique. The problem that they had around the house was how to locate one another. So there were various devices around that indicated where the other one was, since they were both deaf and blind. But they could speak to each other, just, hands on the faces. And this guy had a job. He was a tool and die maker, which he held down. He came to Boston alone, flew to Boston. He carried a card which said, I am deaf-blind, may I put my hand on your face? If he was lost or needed some information, he'd show it to somebody, and they would presumably say yes, and then he would be able to communicate with him. He could talk, it wasn't completely, wasn't perfect. He couldn't monitor his own speech production, so it tended to degrade, and he had to get continued up training to keep it up. But it was intelligible, and he could understand what anybody else was saying. And that's the way he lived, an almost normal life. And he wasn't the only one. There was a fair number of them. And that's a case that shows, these are cases that show quite remarkably how little information is required to get the whole language system operating. It's normal language use is dramatic enough example of the absurdity of believing that language is taught. But these cases show with extreme strength that it's just total nonsense to think that some kind of instruction from the outside determines the major course of language growth. At the very most, it can provide very peripheral information. On the matter of there's some information here about the critical period too. On the matter of critical period, it turned out in the population of people that they were dealing with that there was success in teaching language by this method only if the deaf-blindness had occurred after a certain age. I think it was about 16 months, meaning that the children had already, they weren't speaking yet, but they had exposure to language. And somehow that exposure to language must have set something in motion too, which could then be built upon in the by the course of this training. The same was true of Helen Keller, the famous case of deafblind. She was deafblind after an age roughly like that. And it may be that being deafblind from birth would kill off the mechanisms very much the way that blindness in a kitten kills off the visual mechanisms. In the face of the general evidence about language growth, of which there's plenty, it takes considerable dogmatism to believe that conditioning could have anything to do with it. And in the face of evidence like this, it becomes outlandish, to believe that conditioning may be a factor in language growth. And as more cases of this kind come along, it may be possible to sharpen and narrow down quite precisely the kinds of stimulation that get the system to operate and the kinds of sensory inputs that are required to get it moving. There's now work by people who are involved with sensory aids, which may shed some further light on this. There's a thing in the ear called the cochlear membrane, which receives signals and is stimulated along the course of the membrane, depending on the frequency of the incoming sound. And there are an obvious idea, which people are trying, is to make an analog of the cochlear membrane and simply put it on some other part of the body. So maybe on the stomach or on the arm or something like that, and see if, and then arrange construct the analog so that it provides stimulation given a certain sound exactly in the manner that the cochlear membrane would to the auditory nerves. And then see if the human nervous system is flexible enough to adapt to signals coming from some other part of the body that have the same structure as the signals that tell the auditory nerve that it's a sound with a certain structure. If this works, which nobody knows, it would be possible to for a person who's, say, deaf to hear something like hearing with a device implanted on some other part of the body. There's a little evidence that something is working out, but nobody knows much about it. And doubtless there'll be more inquiries of that sort. Well, let's continue on the course that we were following. Going back to yesterday, I ended up by talking about the question of unification, which is an obvious question for a naturalistic inquiry. We have these studies of the mental systems computational representational study, theories of language, for example, there are cells in the brain. Presumably there's some relationship between what the cells are doing and what these computational systems are doing. If we accept the plausible view of the post-Newtonians, people like Lamettrie and Joseph Priestley, thought or language is just a property of an organized system of matter, and presumably in this case this means some organization of cells. So presumably the generative procedure and the the performance systems and so on are a property of a complex property of some arrangement of cells, and the question is, how do you fill in the blanks in that description? That's the unification problem. And I mentioned that there's some connections here and there. Perhaps most surprising ones are the correlations of categories of linguistic structures with electrical activity of the brain that I mentioned. But there are huge gaps. And I mentioned a few ways in which people try to overcome their feeling of discomfort with those gaps. Notice the feelings of discomfort you don't have to share. There's no particular reason for discomfort. There are a lot of things we don't know about, and one of them is how to fill in this gap. Not more shocking than other things. But a lot of people feel that there's a special problem here, something special involving the mental, let's say. And among the ways of trying to overcome that feeling, there is, I mentioned the slogan that we should consider the mental to be not to be the neurophysiological at a higher level, which is just dogmatism. We don't know that it's the neurophysiological that's relevant, and there's no evidence about it. I suggested that slogan ought to be rephrased as the slogan, we might speculate that the neurophysiological is the mental at some other level. Maybe it is, maybe it isn't. Another approach is what's called eliminative materialism. We should stop studying the mental altogether and study the material world. That will become a substantive proposal when somebody tells us what the material world is. Short of that, doesn't mean anything. I mean, the mental's part of the material world, so eliminative material, since there's no other world. So that doesn't sound, when people use the term, speak about it, and argue about it, but it's hard to see how that's a substantive proposal at all. An associated proposal is that psychologists and linguists and so on should stop studying cognitive processes and language and should start studying neurophysiology, which is just craziness. I mean, it's like saying that embryologists should start studying quantum theory or something like that. That makes no sense, of course. Another view is that we should try to think in terms of connectionist models, which I loosely describe, but their important point is that they don't have any explicit rule following in the way that an ordinary computer program or computational system does. And maybe somehow they'll do something. Again, it's pretty irrational. There's no reason to believe that these processes, that these abstractions from the nervous system select the right properties or that they have the right kind of structure, and there's no explanatory success in using them. The major approach, and the one I want to turn to now, is the idea that we don't really have to feel uneasy about the mental because we have good, hard-headed, solid, substantive examples, robust objects which have mental properties, and nobody worries about these, so therefore we don't have to worry about humans. And these robust objects are computers. The idea is that modern computers carry out our physical objects. Everybody agrees that your personal computer is a nice, robust, solid physical object, and it does execute software. And if all the mental processes is software, algorithms, procedures for doing something, then the computer's doing it. So there can't be anything mysterious about it, because these are just physical devices, and now we've overcome the problem. Well, that view that psychology studies software problems, as I mentioned earlier, that view was coming forth about the mid-1950s, and it was certainly part of the so-called cognitive revolution. And in some respects, it was a kind of a liberating idea. You have to recall that this was a period when psychology meant the study of things like conditioning, which probably doesn't even exist, or learning theory, which was a total fiasco that had achieved nothing in a century. The various branches of psychology were more or less designed in terms of one or another dogmatic assertion about what kind of theoretical posit you were allowed to make, which is all obviously total nonsense. So the field itself was totally stultifying. And to come along with an idea that allowed some work to be done was exciting. Hence the idea that the study of cognition is really the study of software problems. Made it possible to open up a lot of topics for inquiry. And that was part of what led to what many call the cognitive revolution. In retrospect, it's less obvious that this was such a great move, and because it brings along with it a number of serious conceptual problems that don't arise if we just approach the subject in a straight naturalistic path, along a straight naturalistic path. The first problem that arises has to do with the nature of artifacts, things that are constructed. So I don't know, it's like take, say, this thing over here. I think it's a table. Okay. If somebody asks me what it is, I'd say it's a table or a desk. Am I right? Well, in order to answer that question, it's not enough to do a full investigation of this thing. I mean, you can understand every physical property of it and not know whether it's a table. I mean, maybe I just think it's a desk and a table, and it's really a hard bed for a dwarf who comes in here every night and goes to sleep over here. And maybe it was designed for that purpose. That's the designer's purpose, and that's the way it's normally used. And it just happens that, I walked into this room by accident and mistook it for a table, so I'm sitting here. That's perfectly possible. If that was the designer's intention, and that's the standard use, then it is a hard bed. It isn't a table. So whether it's a table or a hard bed or some other thing depends on the intent, at least on the intention of the designer, and the customary use and the functions that it serves and so on and so forth. That is, what it is depends on how it's placed in a very complex framework of human concerns. Okay. Now, no physical object can have those properties. So when we talk about this thing, it's not this thing isn't a perfectly fine physical object. It's just that what individuates it, what identifies it as a so-and-so, say a table or a bed or something else, that individuation, that identification, is relative to specific human cognition. Specific properties of human cognition has nothing to do with its nature. A Martian lacking our concerns and interests, who knew all the physics we knew, would know everything about this that we do, but wouldn't know whether it's a table or a desk, and in fact couldn't ask the question, because he wouldn't know about things like intent and design and use. And that's true of all artifacts. It's not true of natural objects. So whether something's a nematode or not is independent of the designer's intent, because there wasn't any designer, and it's independent of its function because it doesn't have a function, or how you use it, like maybe you use it to poison people or something. That's independent. That doesn't affect whether it's a nematode or not. So there is a basic difference between objects of the world and artifacts. This was well understood as far back as Aristotle. If you look at Aristotle's classification of objects into, idea, causes, it's usually translated in English. I don't know what they do in Spanish. But the factors that enter into making something what it is, they include intent, function, structure, constitution, number of different things, and what an entity is depends on how it's placed in this framework. Now, Aristotle thought about this as a metaphysical analysis. And we might prefer today to think of it as an epistemological analysis or a cognitive analysis. That is an analysis of how human intelligence organizes the world for its own purposes. But the story is about the same. And in fact, one of the, in my opinion, best theories of semantics that's around is by a, not developed much, but suggested by a philosopher named Julius Moravcsik, who was also a classical scholar as well as a modern philosopher, and he described it as the ideational theory of semantics, meaning a theory of semantics that takes the Aristotelian factors, idea, and uses them as semantic categories, suggesting that Aristotle was just intuitively picking out the properties that humans in fact use, like, say, function and purpose and so on, and so, and intent and so on, and categorizing objects that way, and that's the core of human common sense natural language semantics. And he gave a series of examples that illustrate that that's plausible, and I think it is plausible. Actually, it's kind of striking that when you look at contemporary work in philosophical essentialism, work that grew out of originally Saul Kripke's Naming and Necessity, which gives arguments that I don't think are very convincing about the essential nature of entities. It turns out that his essences are virtually identical with the Aristotelian idea. So being a table is the essence of this thing, if it is a table. Okay, it's an essential property of it in Kripkean essentialism. And that just seems to me a very misleading way of saying that as human beings, we categorize things in terms of a space of human interests, which includes things like designer's intent. It doesn't tell you anything about the essence of this object. I mean, its essence is just, it's what it is, what it's made up of. That's its essence, period. Its being a table is something about our interpretation of the role it plays in our lives, let's say, nothing more than that. This, incidentally, is one reason why, trivially, obviously, the natural sciences are going to depart very far from human common sense. I mean, the natural sciences are not going to have in them any notion like being a table, say, which will hold of this or not hold of it, depending on what its designer intended. And that's not going to be a concept of physics, for example. Now, this is true of every artifact. So, for example, suppose it's also true of artifacts that are designed to do something, like take, say, a key, to open a door. If I ask for a key to the door of the room of the hotel that I'm staying in, and they give me a thing, and I try it in the door and it doesn't work, did they give me the wrong key? Did they give me a key that malfunctions? Did they give me something that wasn't a key at all? Well, there's no answer to that, generally. It depends on the purpose for which it was designed and for which it was given to me. If the purpose of the guy behind the desk was to cause me problems, then the key is functioning perfectly when it doesn't open the door. It's not malfunctioning. You can't tell whether an artifact is malfunctioning by looking at what happens when you use it. You have to place it in a much richer framework of human concerns and intentions, including things like designer's intent, or intent of people who are involved in providing it in this case. And that's true for all artifacts, and it's of course true for computers. Coming to computers, computers are artifacts. They're designed to do something. Suppose somebody gives you a software, suppose you want a program to, say, add numbers. You want a calculator in your computer, and somebody gives you a software program which adds numbers. And suppose what it adds is what Kripke called the plus function, which is different from plus. It's like plus for everything except, I forget what, say 2 numbers for which it gives the wrong answer, maybe 5 times 25, it gives 139 or something like that. But the rest of the time it gives the right numbers. Well, is the program malfunctioning? Well, again, it depends what the intent was of the software designer. it's functioning quite perfectly if he wanted you to get the wrong answer when you multiplied 5 times 125. Or it's functioning perfectly if he had another function in mind, which didn't happen to be plus, just happened to be identical with plus for all points except this one. And again, there's no answer to the question whether it's functioning properly or malfunctioning or following a rule or not following a rule or whatever. It's just doing what it does. And we interpret it as following a rule or not following a rule or functioning properly or malfunctioning, depending on the space of intentions and goals and purposes in which we place the object. But the question of whether, say, that software program is failing to follow the rule of addition, or multiplication in that case, if it's failing to follow the rule, that's a meaningless question. It's failing to follow the rule only if it was intended to follow the rule. Then it's failing to. But there's nothing in its nature that tells you whether it's failing to follow a rule. Now that's going to be true of computers quite generally. Furthermore, in the case of artifacts, like say computers or keys or desks, there is no natural kind. There's no kind of things, there's no kind of nature, category of nature into which they fall. Just about anything could be a computer. A pile of sand on the beach could be a computer if you give it the appropriate interpretation. You interpret the arrangement of grains in such a way that it's calculating numbers. You can always do that. Anything could be a key for a properly shaped door. Like this thing could be a key for a door that was made in a crazy fashion. There's no whether something's there's no natural kind. There's no normal case. There's no normal case from which other things are deviations. Again, that's quite different from a natural object. In the case of, say, a nematode or a cell or a giraffe or something, there's a natural kind, a kind of nature. And there could be a word, at least in science, though not in human language, in my opinion, but in some created scientific language, there could be a term that picks out that natural kind, like, say, nematode, and there could be normal instances of it, and it would make sense to talk about deviant instances. For example, it makes sense to talk about a nematode with a genetic defect. Maybe, it was hit by a cosmic ray or something, because there is a normal nematode, and we can therefore make comments about the category of nematodes. But we can't make comments about the category of computers, because anything's a computer, just about, maybe anything, if you have enough imagination. Similarly, when you look at a computer, you can't really tell what's the hardware and what's the software. I mean, with enough further assumption, it's not that, some of the chips are labeled software. Anything, what software could be distributed around the computer chips in any crazy fashion. If you add further assumptions, like you add some assumptions that say only certain kinds of change, if you consider only certain kinds of modifications of the computer, like not hitting it with a wrench, but sticking a disk in the disk drive. These are just two different modifications of the physical object over there. And if you restrict yourself to one category of them, like sticking disks in the disk drive, then relative to those decisions about what kind of interferences with this object you're allowed to make, relative to those quite arbitrary decisions, you can distinguish software from hardware. But that's, again, relative to human concerns and interests. The computer itself doesn't know anything about hardware and software. So we have, when we move from the study of the mind, some property of organized matter, like, say, valence or the properties of electricity and magnetism are properties of certain organized matter. When we move from that to computer models, we've moved from the frying pan into the fire, in the standard English idiom. I assume there's some similar idiom you can make up. The frying pan was quite, is that intelligible, or somebody want to translate it? Okay. You've moved from a problem that's, that's manageable to something that's completely unmanageable, which introduces inherent complications that don't arise in the case of the study of thought in the first place. Now, the belief that there was a problem about the mental was a mistake. There was no inherent problem about the mental other than our lack of knowledge of what it is. But that's a problem that holds all throughout the sciences. A lot of things you don't know what they are, and you don't know how they're connected to other things. There was no special problem. So that was a mistake in the first place. But this effort to resolve the problem just adds further difficulties, new additional difficulties that didn't arise in the first case. In the case of, say, language, it is a natural kind, like just as nematodes are. It has a normal case. It's not a matter of our decisions whether rules are being followed or not. It's just a fact about the system. Like it's a fact about the visual system that it's processing in a certain way. There was no designer's intent because it's an object, not an artifact. There's no conventional use because there's no use at all. It has no primary function because it has no function. Things in the world don't have a function. We assign them functions because of the way we choose to look at them. So it raises none of the problems that computers raise. And therefore, using computers as a robust model to make you feel happy about the mental was from this point of view, a mistake to start with. It's a mistake that shouldn't have been made. And I think it's a mistake that arises only if you fall prey to dualistic temptations that lead you to feel that there's something special about the properties of organized matter that we call thought that does not arise in the case of properties of organized matter that we call electrical attraction repulsion, let's say. Okay, and there isn't, just other problems, but not problems of a special nature, at least from a naturalistic point of view. I'm assuming throughout a naturalistic point of view. If you have a dualistic point of view, of course, it's different. Well, moving on to the cognitive sciences, and again, let me make the distinction between the empirical studies, like somebody's study of visual processing, and the theoretical inquiries into the nature of the subject, the more philosophical side. I'm now talking only about that. In the latter kind, some rather curious moves have been made which follow from picking computers as the model and thinking of the mental as software problems. Okay. Notice you're led very quickly to a conception of the mental as being whatever can be computed. Okay. So, as it's put in the AI, artificial intelligence literature, mental activities are just the carrying out of an algorithm. Okay. Mental activities are the carrying out of an algorithm. An algorithm is just a computer program in effect. Okay. So mental activities are the carrying out of a computer program. In fact, many advocates of AI, artificial intelligence, argue that thermostats have mental activities because they are carrying out a kind of, these things that measure the, turn on the heat when the temperature reaches a certain point, that they're carrying out a certain algorithm in particular way, so therefore they have mental activities. And computers have mental activities, or at least would if they had enough achievement. I mean, it's often suggested that they have to achieve a certain amount before we are willing to attribute to them mental activities. This gives you a different approach to the mental. In fact, this is another form of dualism. It's treating the mental in some fashion quite different from physical things, from the physical world. And it leads in strange directions. I mean, instead of thinking of, say, eye language and properties of eye language and so on as states of the brain, sort of mental organs, if you like, which are just like any other organ, except they have to be aspects of the brain. Instead of thinking about things that way, what you do is move over totally to the computational level and consider what can be done by a computer program. Now, if you're not inclined to say that thermostats have mental properties, and many people are not, you'll add certain performance criteria. And you'll say that an algorithm has mental properties only if it satisfies performance criteria. And the standard performance criterion, the one that sort of dominates the literature is what is called the Turing test. Alan Turing was I don't really know enough about people's background to know what to explain and what to not bother with, so everyone know what I'm talking about? Or, well, Alan Turing was a very important mathematician of, around the middle of the century, who, among other things, did some of the essential mathematical work that led to the design of modern digital computers. And back in 1950, he wrote a kind of classic article in which he proposed what has since been called the Turing test. In my opinion, his article has always been misunderstood. I don't think people have read it correctly, or maybe not read it at all, and I'll come back to what he actually said. But let's begin with what he's thought to have said, okay? And that's the only thing that influenced the field, not what he said, but what he's thought to have said. What he's thought to have said is that if a machine, the term machine is just a word for program. They're interchangeable. Any computational type machine that somebody builds is a program for what's called a universal machine. And a universal machine is not very exotic. Every one of you who has a personal computer has a universal machine with one proviso. You have to be able to stick an infinite number of possible disks in it to keep building up the memory. But if you've got an infinite source of additional memory instead of just a finite source, it becomes a universal machine. In fact, it becomes what's called a Turing machine. And any program for such a machine is a possible machine on its own. And any possible machine on its own is a program for that machine. That's what it means for the thing to be universal. So any algorithm that exists, any possible algorithm, is a program for your computer if you idealize to infinite memory. Okay, that's basically what it comes down. It's good enough. It's not exactly accurate, but good enough for our purposes. The Turing test, what Turing's alleged to have said in this story is that if you take, he designed the following test. You have, say, a screen, and over here you have a person who's a judge. So let's call that the judge. And behind here you have a person and a machine. Machine just means some algorithm for a computer. So over here you have a piece of software, piece of software with a computer that runs it. Here you have a person, here you have a judge. The judge is allowed to communicate both to the person and to the machine in the same way by, say, typing something in at a keyboard that the person or the machine picks up at the other end. And then, so the judge is, say, allowed to ask a question of both the person and the computer. And then the person gives an answer, types in an answer, it comes back to the judge. The computer program does whatever it's designed to do and types out a response. And that goes back to the judge. And if the judge can't tell which is the person and which is the machine, if it's confused, in other words, and mistakes them, in that case, the machine has passed the Turing test. Okay, that's what it means to pass the Turing test. And what Turing is alleged to have said is that if a machine passes the Turing test, it thinks. Okay, that all human intelligence is the capacity to pass the Turing test. That is to fool somebody into thinking you're a person. Okay, like a Martian comes down and fools us to thinking it's a person, then it thinks. Notice that's a completely non-naturalistic idea. This is a radical shift from, say, the 18th century Lemaitre and Priestley. For them, thought is a property of matter on this earth. It's a property of particular forms of organized matter, like people. That's what thought is. Just as electricity is a particular property of certain forms of matter. The fact that you might be able to create something out of non-earthly matter that has properties that look like electricity wouldn't have any bearing on what electricity is. Okay. The idea that you might be able to fool somebody into thinking that something's, a duck, doesn't tell you it's a duck. Okay. Because To be a duck is to be a property of a certain kind of matter. But this is totally different. Now the mental is the mental regarded first as the computational. That's the first step. And then, if you're unhappy about thermostats being mental, the computational be sort of sophisticated enough computational, where sophisticated enough is spelled out in terms of the Turing, passing the Turing test. That's a completely different conception of the mental, and the mental now becomes a property unlike any property known in the natural world. The mental is defined by a certain performance criterion. Okay, there's a certain performance criterion that's stipulated, and any class of objects, or maybe any class of objects built out of certain kinds of components, that passes that performance criterion has this property. There are no such properties in the physical sciences. You think through physics or chemistry or something like that, there's no property, there's no category of entities identified in terms of their satisfying certain performance criteria. I mean, you may use performance criteria as tests for some property, like you may use a litmus test for determining whether something's an acid or a base, and you may rely on that test enough so you start calling it a definition. But the fact of the matter is that being an acid is not defined in physical theory as passing the litmus test. Okay, it's whatever it is, and it happens to pass the litmus test. In fact, performance tests don't exist in the sciences. They're just, but there are operational criteria and so on. So this is something entirely new and entirely non-naturalistic. Again, I'll qualify. I don't think this is what, in fact, it's clear that this is not what Turing was saying, but this is what he's interpreted as saying. Notice that the Turing, when you talk about the Turing test, that's misleading, because this, what I just described, is not a test. It's an indefinite range of possible tests, depending on exactly how you set it up. So there are all kind of different ways of setting this up. When are you going to decide that the judge is fooled? All kinds of things. And only if you answer all those questions do you have an actual operational test. So the so-called Turing test is a class of possible performance criteria, and according to the computational approach to mind, we've sort of now gone from, remember the course we followed, we start from feeling that there's some problem about the mental because we can't explain it in terms of cells. Different than the problem about, say, chemical elements in the 19th century, when you couldn't explain them in terms of particles and fields. There's some different kind of problem about the mental. We start with that. We try to resolve the problem by saying, well, we have robust objects around that have mental properties, namely computers, so there's nothing mystical, it's not ghostly. We then identify the mental with the software aspect of the computers, overlooking the fact that that's not a physical distinction. It's a distinction we make in terms of a class of interests and concerns. And we then identify the mental with computational or the sufficiently sophisticated computational, meaning passing some variety of the Turing test. From now on, I'll just call it the Turing test, although, as everybody does, although bear in mind that that doesn't refer to anything. It only becomes a test when you fill in a million blanks that are left open. Well, it now turns out that when we're studying the mental, we don't really care what the physical realization is at all. See, now we have a distinction between mental and physical. I mean, the mental is just abstract computations. It's some mathematical thing. And the physical form in which the computation is carried out is irrelevant to the study of the mental. Okay? We're just studying certain algorithms. And they can be carried out any way you like. It doesn't matter how. Okay? And we're assuming that it means something to say what I just said. I don't think it means anything, but I'm granting for the purpose of discussion that it means something. We're assuming that there really is an identifiable category of software versus hardware in computers, independent of our interests and concerns. And I'm assuming that it is really possible to pick out in the world what is a computer. And I don't agree that any of that is possible. But to continue with the discussion, let's grant it so we can pursue the debate and discussion of artificial intelligence and cognitive science. Well, we now study algorithms, that is, the mental, in abstraction from any form of material realization. And that becomes psychology. Psychology is now the study of algorithms, cognitive psychology at least. And that's the way it's usually considered, in fact. I'll give some quotes from a particularly lucid exposition of it by Ned Block, a colleague of mine, in an encyclopedia of the cognitive sciences, 3-volume encyclopedia of the cognitive sciences. It was just published by MIT about a year ago, in which his section, his chapter in the encyclopedia is on the computational theory of mind. Okay, psychology taken as the computational theory of mind, the computer level of the mind. And here's the way he defines it accurately. This captures the field. He says the computer model of mind is a level of description of the mind that abstracts away from biological realizations of cognitive structures. Now, here we have to be a little cautious, because there are a lot of different ways of abstracting away from something, and we have to make sure which one we're talking about. For example, abstraction away from something may be what we may call contingent abstraction. Like we may study something abstracting away from some of its other properties because it's useful to do so, or because we don't know enough about those other properties to look at them, so therefore we have to abstract from them. That's contingent abstraction. We're doing it for a particular purpose or because of a particular lack of knowledge. Okay, like you might decide to study the planets, as mass points following certain laws, abstracting away from the question of whether they're made out of atoms and molecules or some other thing, or whether they have mountains on them or don't, or whatever. That's perfectly intelligible. That's contingent abstraction. That leads to a certain field of mathematics, called rational mechanics in this case, which you can investigate because maybe it teaches you something about the planet. So that's one kind of abstraction. I don't want to talk about it. I guess another kind of abstraction that we might consider is what you might call exploratory, which is often done. We take some complicated system, too complicated to study, and we identify certain properties of it, and we say, okay, I'll just study those properties. Maybe if I just study those properties, I'll learn something. Okay, so you abstract away from the full complexity just to explore. That's done all the time. In fact, every experiment in science does that. You have some messy thing around, and you abstract away from most of the mess, and you look at certain particular things. You, in fact, design your experiment so it yields only those particular things, and then you study them because you hope you'll learn something about the world that way. That's exploratory abstraction. Both of these, contingent and exploratory, are naturalistic. They fall within normal naturalistic inquiry. However, there's a third kind, and that's the kind that's proposed here, and that's what we might call principled abstraction, abstraction in principle. That is, it just doesn't matter how the systems are realized in mechanisms. We're abstracting to something where it just makes no difference what the physical realization is. Okay, well, you might say that this is done in pure mathematics. So when you construct, if you look at Euclidean geometry, say, in a classical period, what was it? Was it a study of the physical world, or was it mathematics? Well, for a long period of time, the answer to that question wasn't a clear question. It was both, sort of. But by the time mathematics got sophisticated enough, it became a clear question. And in fact, it even turned out that Euclidean geometry is not a good theory of the world. But when you abstract Euclidean geometry away from the world entirely, and you go to Hilbert's axiom system, and then you study that axiom system and its properties, then you're doing pure math. And that's abstraction in principle, but of course that's not science at all. That's just pure math. I mean, it may be useful for science, like a lot of things might be, but it's not science, and nobody thinks it is. So there's nothing wrong with principled abstraction. In fact, one might think of large areas of mathematics as that. But here we have something new, principled abstraction in an empirical discipline. Okay, that's something new. And the reason for these side remarks is to make clear how new it is. So we abstract away from, in the study of the mental, in the computer model of the mind, we make a principled abstraction from biological realization. We proceed as follows. We assume certain processors, primitive processors. In other words, we're considering a class of abstract machines, perfectly abstract machines, mathematical objects. And we think of them as being made out of certain elementary components, call them processors. But these too are abstract objects. They are only the formal properties we assign to them. They're not pieces of matter or something like that. So we pick certain abstract processors. In practice, these processors are usually selected, in fact, almost always selected, so that they have what's called universal Turing machine capacity, meaning they're rich enough so that you can construct a universal Turing machine out of them. A Turing machine that can run any algorithm, like your computer abstracted to infinity. Okay, so usually, but though not necessarily, the processors are assumed to have universal Turing machine capacity. We then set up a performance criterion like passing the Turing test or something else. And we consider the class of objects, so the set of all objects K, all is abstract, class of all objects K, such that K is, let's call this P and this, not so good, C for criterion. K is constructed out of P and satisfies C. Okay, so to put it simply, we pick some set, the primitive processors are just anything at all that has whatever properties. To identify the primitive processor, we just give its properties. And anything at all that has those properties is a primitive processor. Whether it's made out of the materials that exist in the universe or in some other universe or imagined universes or whatever. Okay, doesn't make any difference. We set up a performance criterion, which could be anything you like. Let's say, performance criteria are completely free for the asking, so you can pick up any one you want. The ones that are usually looked at are some version of the Turing test. We then consider the class of machines, the class of abstract objects, the class of programs, the class of algorithms that are constructed out of these processors, that is, that can be put together out of elementary elements of any kind whatsoever that have the properties of the processors and that pass the criterion, satisfy the criterion, and that's psychology. Okay, psychology is that study that I've just identified. Now, there's usually another thing added here, and that is that people have to be in here. Okay, it's not obvious why, incidentally. This looks completely arbitrary. That you have to include people. It's not clear what they're doing there at all. The study would certainly be a more elegant form of, it's not mathematics, again, because there's no theorems or anything like this, but as an abstract inquiry, it doesn't seem to make a lot of sense to put people in there, but that's usually assumed tacitly, that the performance criterion is one that people pass. Okay, so that's usually added on, but as I say, irrelevantly. And to continue with Bloch's description I've just been describing, let me continue with his quotes. For cognitive science, it does not matter how the primitive processors are realized. They can be realized in gray matter, parts of the brain, in switches, in little creatures running around, like you could imagine mice pulling strings that make something work, in other kinds of matter that don't exist, but that we could imagine, in imagined kinds of matters that might exist in some alternative universe, whatever. That's what the primitive process would be, as long as the thing, and we don't really care at all how they're realized. We only care about their properties, and we're interested in whether the software built out of those entities, so that its structure can reduce to these properties, can pass the performance criteria. And if it does, it's part of the class of machines we're concerned with, as long as humans are also part of it. He goes on to point out correctly that psychology is not a biological science. It's not part of biology, which is certainly correct. But psychology is not a biological science. Furthermore, given the anti-biological bias of this approach, if we can construct automata in our computational image, which means automata that do like we do relative to a performance criterion, if we can construct automata in our computational image, performing as we do by some criterion, then we will naturally feel that the most compelling theory of the mind is one that's general enough to apply both to them and to us, as distinct from a biological theory of the human mind, which would apply just to us. Okay, that's the crucial difference. And he wants to insist on this because of what he says is the common, though mistaken, idea that psychology is a biological science. And according to this, it isn't. It's not part of biology at all, so of course it's totally non-naturalistic. Okay? I mean, it's not hidden here, it's explicit. Okay? It's non-naturalistic, it's not a biological science, it's not part of the study of the natural world at all. An imagined form of matter, which had the right properties, would be perfectly good as a realization, because we're only interested in the software and the mathematics. So the computational model of the mind is now some new form of intellectual inquiry. Psychology is some new form of intellectual inquiry, divorced from the sciences, which is considered with certain categories of abstract systems that satisfy certain performance criteria, and for unexplained reasons, humans come in at this point. Yeah?
Not unexplained reasons at all.
I don't agree. Why?
You cannot mention only the criterion of passing the Turing test, because there are stupid programs that can pass the Turing test. Bloch himself, in the same paper that you are quoting from, shows how to do that. That's why you need to mention anyway.
No.
That's the reason.
No, see, the Turing test crucially mentions persons. There's no question of see, if you make the criterion the Turing test, then persons are there, because the Turing test is defined in terms of persons. Remember what the Turing test is. The Turing test is a test to see whether a judge can distinguish a machine from a person. Okay. To put it differently, sorry, I put it backwards. A machine passes the Turing test if the judge can't tell it from a person. So if your operational criterion is the Turing test, it's obvious why persons enter, because the Turing test is defined as being indistinguishable from a person. So of course persons enter. But the question is, if we are allowed arbitrary performance criteria, it's not clear why we have to design one that involves persons.
The question is whether or not to implement a program that passes the Turing test is enough to have mental properties.
Well, it is for AI.
No, it's not enough.
For AI, it's enough.
No.
Yeah, well, look, I mean, let me give you a concrete case. Just last November, I'll give you an example. I'll give you an example. Last November, there was a test carried out by the Cambridge Computing Society, and Boston Computer Museum. there's a $100,000 prize that was offered for the first program that'll pass the Turing test. So they ran the first test last November. The thing was run by Dan Dennett, who's a well-known philosopher and cognitive scientist. The main judge was Quine. Bloch was one of the observers, and a whole bunch of distinguished computer scientists and artificial intelligence people and so on took part. And in fact, I'll describe what happened, but the idea was that if a program would pass the computer, none of them quite passed the Turing test, that if a program did pass the Turing test and would fool people, then indeed there would be no reason not to say that it has a mind. Now, Ned Block himself is sort of skeptical about this for various reasons. So speaking of him as a person, yes, he's skeptical. But the field takes this as the definition. That's AI. In fact, strong AI takes an even stronger position, which includes thermostats. Okay, but weak AI is the position that the mental is the computational, just as Bloch designed it. And then you pick a performance criterion. And the usual criterion, the criterion that defines the field of artificial intelligence, is the Turing test. Personally, I agree it's total nonsense, but that's the way the field is set up. That's why distinguished people showed up to be judges in this competition. Incidentally, just to tell you what happened, the programmers were allowed, the people who programmed the machines were allowed to select the topic that they had a jury, not one judge, but like a jury of 10 people or something. And the programmer the person who submitted the program was allowed to select the topic of the questioning. So, one person picked Shakespeare and one person picked, I don't know, something else. One person picked, we were trying last night to find a good translation for this in Catalan, but nobody could figure it out. In English, it was whimsical conversation. I don't know if anybody figured out the right translation yet, but what it means is conversation that is just kind of light and a little comical and has no point to it. Is that what it is? Okay, so that was the winner. And the way the program was designed is it produced cliches at random. Okay, so you push a button, the questioner asks something, and out comes some cliche picked at random. And then you ask something else, and out comes another cliche picked at random. And people were pretty much fooled. A lot of people thought, yeah, that's a person carrying out a whimsical conversation. And maybe if you sharpened it up, you could fool more people. So that won the prize. That won $100,000. And I should say this is enough already to show that the whole business is total absurdity. I mean, it's not that anybody ought to be taking this seriously, but it is taken seriously. That's why all of this stuff goes on. That's why you have a field of AI and strong AI. That's why people like, say, John Searle, to whom I'll return in a moment, gave an argument against it, which now, has led to a huge debate with Dennett and Hofstadter and all sorts of others. Ned Block personally is skeptical, but the account that he gives of the computational theory of mind gives no basis for skepticism, because he has no sharper notion of performance criterion. He doesn't offer a tighter notion of performance criterion, either in that article or anywhere.
And that this thing that you said, for unexplained reasons, these people, these guys like Network, etc., mention people in the definition of what is to be intelligent, or to think, or to satisfy mental properties. And this is not true. Simply that. This is not true. It's not for unexplained reasons.
What is the reason?
The reason is that you cannot give as definition to have to think or to satisfy mental properties just to implement a program that passes that.
Why? Oh, no, but see, when you bring in the Turing test, you beg the question. Because when you bring in the Turing test, you've already explained why people are part of it. Look, the Turing test is defined in terms of people, okay? So once you use the Turing test as your criterion, you have explained why people are part of this. namely your criterion is the Turing test, which uses people. But the question is a different one. Why the Turing test should be the criterion? Why not some other criterion?
You need to mention people for the following reason. There are foolish programs that are able to pass the Turing test.
Yeah, like this whimsical conversation program.
Yeah, I mean, you can formal ways you can define network that.
If he had done that, he would have won $100,000 at this competition.
No.
Yeah.
What I'm saying is that this program can speak about is not realizable program.
Oh, okay, fine. We're only talking about realizable programs, of course. We're talking about programs that are realized in terms of the processors. Sure, we're not talking about unrealizable programs. That we throw out. We're talking about programs realized in terms of the processors. That means realizable programs. And if somebody knew how to do it, they would immediately enter the, if you think you know how to do it, enter next year's competition and you'll come out with $100,000. I mean, no matter how stupid it is, that's worth doing. The fact of the matter is, I want to stress how seriously this is taken. The National Science Foundation gave $100,000 or something to support this. It's got all kind of foundational support behind it. It's got a huge raft of major people in the computer sciences and philosophy and so on participating. There's a fringe of skeptics. It's not everybody. Like there's a guy in the Harvard Computer Labs who wrote a critical comment on it and so on. And Ned himself, who was one of the observers, thinks it's a joke. But it's taken very, very seriously. In fact, Dan Dennett, who is the organizer and who certainly takes it seriously, made some comments that sound ludicrous, but it's not so obvious why they're ludicrous. He said that if there was a program that really passed the test, if somebody, this was before the test was run, if somebody submits a program that really passes the test, he says that's going to raise serious moral problems. For example, are we allowed to unplug the computer afterwards? Since this computer now has mind, because mind is, after all, just being able to pass the test, would it be immoral to unplug the computer? Actually, that's the wrong analogy. The question is, would it be immoral to reformat the disk? It doesn't matter whether you unplug the computer or not. It sounds ridiculous, but if you've gotten as far as Ned Block's article, thinking of the computer model of the mind as a non-biological subject and having mental properties like, the properties that make us moral agents or whatever, as being purely computational properties, then the question does arise whether you're carrying out an immoral act if you reformat the disk. In fact, even deeper problems arise, that he didn't discuss and that others didn't discuss, and that is, why shouldn't all the people who participated in this already be jailed? The fact is that the programs that were given performed much better than monkeys did, and nobody would reformat the brain of a monkey after this. In fact, if you did, it would be a criminal offense. There are laws about proper treatment of experimental subjects. And in fact, experimental subjects have to sign consent forms. None of these programs sign consent forms. So in fact, everyone who participated in the experiment is already in violation of law if having the psychological properties of a person, the properties that make us subject to moral judgment, to moral decision, and so on and so forth, if they are simply software problems. And that will be true if psychology, that is the study of the mental entirely, is a purely computational study, divorced in principle, remember, divorced in principle from any biological or physical consideration. If that's the way it is, it's hard to drop these questions. And if the questions seem ludicrous, as they should, then you have to ask, A, why do serious people get involved in it? And B, what went wrong with the argument? Because something must have gone wrong with the argument. Go ahead. I'm sorry I interrupted you. Yeah.
You basically criterion of what is to think or to have mental properties is behaviorist point of view. It's very misleading. If you put in the these guys don't
what does Ned Block believe is the criterion?
Is to have some kind of computational, functional structure similar to the structure people have.
But you know, he...
That, for instance, is the most behaviorist of recent philosophers. You cannot put him in the same...
Look, he says that it's true you can't put him in it because he doesn't accept this. So he's not in the same category as Dennett, Quine, Dewdney in computer science, McCarthy, and the rest of them. Ned Block himself isn't. But the characterization that he gives of the computer model of the mind is in that category. Because all that's required for the computer model of the mind is that it be built out of processors which can be made out of anything. And then you have to say, well, it has to satisfy some criterion. But the only criterion anyone suggested is Turing's. And in fact, the whole field of AI, both in philosophy and cognitive science, is defined in terms of Turing's proposal and Turing's 1950 paper. That's the whole thing. There's nothing else. I mean, it's true that Block says, look, there's got to be something else, but there's nothing else stated. All right. Let me concede your point, although I don't agree. Suppose that Ned Block has some other criterion in mind. Fine, then let's stop talking about Ned Block. And now let's talk about this field, okay, which has this criterion in mind, namely passing the Turing test. Okay, that's the field I'm talking about. And in fact, that's the only one that I know of that exists. But that's the one I'm now talking about. And that's weak AI. Strong AI says it doesn't even matter if you pass the Turing test. Weaker forms of computation are allowed. Okay? So I'll put aside here the skeptics who think something else is needed. I don't know what. Actually, for a naturalist, it's obvious what is needed. What is obvious is to reject the abstraction in principle from biology. That's what's necessary. See, well, for any naturalist, the mistake was to abstract in principle from biology. In fact, if you do that, you get all kind of craziness. For example, you could make up a field of abstract biology, let's say, in which you set up certain processors that have some of the properties of cells. You take some of the properties of cells, okay, and consider them abstractly, and consider the set of processors that have those properties. Set up some criterion. It can be, if it's AI, it would be a performance criterion. If it's something else, it would be undescribed yet. It would be having some structural similarity to organisms. And then consider the class of all objects constructed out of elements, maybe non-material elements that don't exist in this universe, that have some of the properties of cells and that satisfy some of these performance criteria, let's say getting bigger through time. And then we're not concerned any longer, since we're non-parochial, as Bloch suggests, we're not concerned any longer with physical organisms, to modify his comment appropriately. If we can construct automata in the computational image of biological organisms, we will naturally feel that the most compelling theory of biology, in this case biological growth, is one that is broad enough to apply to both them and us, not just to them and actual organisms. So we'll then be asking questions like whether these organisms grow. Do they really grow, for example? Okay. And in fact, this is just a puzzle generating algorithm. You can do it any way you like. Pick the properties that you like for a set of processors. Pick the criteria you like for success, whether in terms of performance or structure or whatever. Consider the class of all organisms, abstracting in principle from the existing world, that satisfy those things, and then you can ask whether they have some property of things in the material world. Do they breathe? Do they grow? Do they think? Do they talk? Do they walk? Do they enjoy themselves? Do they, have moral rights? I mean, anything you like. You can generate puzzles at will this way. As soon as you make the move of principled abstraction from biology, which carries you beyond the natural. Principled abstraction from biology is precisely what carries you out of the naturalistic world, and then all kind of problems arise. I'll give some examples, and some of them from the actual literature. Okay?
Only for what is war.
Pardon?
Only for what is war. I have a strong feeling that you systematically invent strongmen and misrepresent the position of philosophers. And this is because a basic point. Very clear. You said.
All right. Let's see. All right. Let's see. Is Dan Dennett a philosopher?
I'm mentioning people like or like.
Right. I didn't mention Fodor. Bloch has already made the first error that leads to this, which is why I quoted him. Bloch, as I mentioned, is skeptical. Is Dan Dennett a philosopher? Is Jim Hoagland a philosopher? Is Van Quine a philosopher? I mean, is it? Okay, well, fine. Let's go on with them. Okay, because that's the field I'm talking about.
I think that you have strong arguments against behaviorism.
I'm not talking about behaviorism. I'm talking about people who take Turing to have said that if something passes the Turing test, we should say that it's. Let me go back to what Turing in fact said, since I keep referring to it. Yeah.
I don't know if I understood. You said that if any program or machine passes the Turing test, then it thinks, meaning it can fool people.
That's what the theory is.
So by this criteria, say my performance, my performance criterion is making cars, for example. So I get those robots in a Japanese, in the Toyota factory that make cars. And then, I am asked if this car, if this Toyota 8 is made by the robot, and if this Toyota B is made by the people. And I don't know, because they work exactly the same support.
Yeah.
Then it is, the consequence is that then this machine can think?
No, because remember, this means the judge is allowed to ask any question. The judge is allowed to ask any question about anything. It's not, of course, you could always be fooled in some fixed area, but the Turing test is set up so that the judge can ask any question at all. And if, when the judge asks any question at all, it can't distinguish the person from the machine, then the machine thinks. All right, that's the Turing test. What Turing, in fact, said is the following. And there's a difference between what he said and what the whole range of philosophers and cognitive scientists have taken him to say. What he, in fact, said is, he set up the Turing, he said, we're interested in understanding the mental, we're interested in understanding intelligence, here's the way we ought to proceed. And then he outlined the Turing test, essentially, in terms that I did. And then he said the following. He said, to ask whether machines think may be too meaningless to merit discussion. Okay? But I, Turing, consider that in another 50 years, that would be by the year 2000, educated usage will have advanced to the point, or will have reached the point, where that's exactly what we'll mean by thinking. Okay? So in other words, he said the question of what the word of whether a machine thinks is not really meaningful. Terms aren't well enough defined. He's trying to make them meaningful. Okay? And he says, look, here's the way to make them meaningful. And I think that that's clear enough so that in 50 years, educated usage will have shifted over to that. It's as if somebody proposed a concept of the atom, and he would say, well, look, to say whether atoms really are this is meaningless because, it's not clear enough. But I think that understanding in science will have progressed in another 50 years so that this is what people mean by atom. That's what Turing actually said. Okay? Notice a slight difference between what he actually said and what he's understood as having said, namely that thinking is passing the Turing test. Okay. I don't think you should underestimate the scale of this. This is not only the philosophical and cognitive science literature, it's also the general literature about the topic. So, for example, if you read people like, science writers, good science writers, like, say, Martin Gardner, or the man I mentioned several times, Roger Penrose, who's one of the world's leading physicists, who has a big, fat book on this topic, arguing that in order to deal with these problems, you're going to have to invent some new form of quantum theory. they all define thinking in these terms. That's not even taken in question. Thinking means passing the Turing test. Okay, that's AI. I mean, if they reject AI, they're rejecting this criterion. A lot of them reject AI, but then, you know, not because they're offering some different definition of the mental, but they say that machines won't do it. Machines will never do it. You know? So, for example, when John Searle, I'll give you his criticism of strong AI in a moment, but it essentially takes the framework to be meaningful. Okay? I question whether the framework's even meaningful. The abstraction in principle from biological mechanisms already carries it beyond the meaningful, in my opinion. And that, there is no doubt that that's exactly what, Bloch is exactly correct in saying that that's the crucial step in the computational theory of mind. He says, I was quoting from his article, that the crucial step in the computational theory of mind is the principled abstraction from the biological, which makes psychology not a biological science. Okay? Therefore, there must be other criteria for just about everybody in the field. It's the Turing test, but some other criteria outside that will identify the mental, and we will prefer a theory of the mental that isn't restricted to things like us, as distinct from, say, a theory of flying, which is restricted to birds. Okay? So it's not like the natural sciences, and I think that's the problem. Well, let's continue. Note where this differs from the natural sciences. Okay? One, the natural sciences never abstract in principle from mechanisms. I mean, that's unheard of. You know. So, for example, a natural scientist studying thinking, if the natural scientist, say language or any other kind of thought, if the natural scientist would discover that some specific property of cells, you know, suppose the natural scientist had two theories of language. Okay, here's theory T1 of language and theory T2 of language. And suppose the natural scientist were to discover that this one is realizable in cells of the kind that human beings have. Okay? And this one is not realizable in cells of the kind that human beings have. Suppose that discovery were made. For the naturalist, this theory would be selected and this one would be rejected. Okay? That's obvious. But for the computational theory of mind, it would be irrelevant. Because, to quote again, it does not matter how the processors are realized. Okay? So if they're realized in cells, okay. If they're not realized in cells, not okay. No, it doesn't matter. So the theory of language, which is just part of the mental, for the theory of language, the discovery, the potential discovery that some property of cells, human cells, selects one theory over another would just not be relevant. Language is abstracted away from that in principle. That's one striking difference between this and the natural sciences. A second is that the natural sciences are not concerned about any kind of criteria, whether they're performance criteria, as defines the whole field of AI, or other kinds of criteria like structural resemblance or whatever you want. Such things don't appear in the sciences. If something meets a criterion, whatever it may be, it's of interest for the sciences only insofar as it tells you something about the real objects under consideration. Okay, so if you have some real objects over here, and you set up some criteria of performance, structure, whatever you like, and you find some other imaginable thing, some thing abstractly described that satisfies that criterion, it's of interest only if it tells you something about these things. Well, let's take the case of computer programs again, which, as Herbert Simon, you know, leading figure in the field, points out correctly, was the Drosophila of the cognitive sciences. Why was chess playing the Drosophila of the cognitive sciences? Well, because of a certain variety of the Turing test. See, the particular variety of the Turing test that people have who are studying Drosophila, you know, the Drosophila of the cognitive sciences means, as he explains, the main concern around which inquiry has revolved. Okay, I'm not talking about a minor figure now. I'm talking about one of the leading figures in the field, and nobody questioned it. The main concern around which the field revolved is chess-playing machines, because there's a particular version of the Turing test which will come down to the fact that the machine passes the Turing test if the judge can't tell whether it's Grand Master. Okay. Now, the way you usually check that out is by seeing if the machine can beat the Grand Master. But you can rephrase a competition between a person and a machine and a chess player in terms of a Turing test structure. Can the judge tell the difference between them when it's watching what the two of them are doing? Okay. The thing then is usually turned into the test of whether, how they make out in a game. And that's the Drosophila of the cognitive sciences. Notice how a natural scientist would look at this. Assuming that a natural scientist would want to study chess playing at all. As I mentioned the other day, it's probably not a reasonable topic to study, but assuming that one wants to study that mental activity, chess playing, suppose somebody comes along with a computer program that satisfies a version of the Turing test with regard to chess playing. Say it fools someone into thinking it's a person, does as well as Kasparov or something. First question that the natural scientist would ask is, how does it work? Second question is, how does Kasparov work? Or anybody, whoever you happen to be trying to model. How does Kasparov work? How do people work, if you want to make it more general? Third, does one tell me anything about two? Okay, if it doesn't, then I'm not interested in it. That's abstract. That's contingent abstraction. That's what I call contingent abstraction. You look at, or exploratory abstraction. You study some abstract object to see if it will teach you something about the real things. Okay, if it doesn't, too bad. In fact, chess programs don't, so they're of no interest. The fact that they've been the core of the cognitive sciences, the core around which all research, all general research revolves, that just illustrates the strength of the Turing test in defining the field. Pick some other criterion, you're going to get similar problems. So that's another sharp departure from the natural sciences. And in fact, when you enter this non-naturalistic domain, the questions that arise are pretty odd. Here's a standard one which has been debated for years in the philosophical literature. I'll start by quoting from a sort of classic paper by John Hoagland. In the Journal of Philosophy about 10 years ago. Another paper by another well-known philosopher has been at the center of this stuff. He asks the following. He says, I'm quoting, how might one empirically defend the claim that a given strange object plays chess? Okay. How might one empirically defend the claim that a given strange object plays chess? That's the first topic of his paper about the mental. And he gives the conventional answer. He says, we would properly conclude that this strange object plays. Notice it doesn't matter out of what it's constructed, because we've abstracted away from biology and principles, so that's not relevant. We would conclude, he says, that we would properly conclude that it does if a skeptic is convinced that it meets a certain performance criterion, which he describes, some version of the Turing test. If the skeptic is convinced that the machine meets that criterion, then, he said, we would have empirically defended the claim that the object plays chess. Okay? So the idea is this is an empirical claim, which is a little odd because this is not a part of the natural sciences. But we have an empirical claim which is to which the answer will be that we're trying to defend, and we successfully defend it if the skeptic is convinced by the Turing test that the thing is passing the criteria. Now, the second part of his paper goes on to understanding language, which is what the paper's about. It's called On Understanding Language. And he argues there that we could never meet that criterion. Okay. In the case of understanding language, he gives a bunch of arguments to say that it would never be possible to convince the skeptic that the device is indistinguishable from a person. So the same framework is accepted. We don't have to worry about whether his argument's right or not. The same framework is accepted, but we would have empirically defended the claim because the skeptic would never be convinced. Okay, so therefore the machine is not understanding language. Notice the crucial point. It's an empirical claim, and the claim is correct if the performance criterion is satisfied. Okay, same basic argument. There's actually been a huge debate about this over the last 10 years or so. Just not. Go on. Yeah. 5 minutes. Yeah. I'll just describe the debate and talk about it tomorrow. There's been a huge debate. One of the dominant debates in philosophy of mind and cognitive psychology was initiated by John Searle, who wanted to show, he wants to debunk all of strong AI, the whole AI field. And he raised the following question. I'll just describe the experiment and then you can think about it, and then we'll go on. He said, suppose we had an algorithm that understood Chinese. Okay, let's imagine that somebody could construct an algorithm that would understand Chinese by whatever performance criterion you like. Okay. Now suppose that you make a room, and in it you put John Searle. Okay, John Searle, by assumption, doesn't understand any Chinese. Okay, he actually sets this up in Turing test terms, but I'll skip that to save time. You feed in. Suppose that the test you're trying to provide is you give a question in Chinese, and you're supposed to give an appropriate answer in Chinese. All right, so like the Turing test. You give a question, you're supposed to give an appropriate answer. Suppose you feed the question in. John Searle has lying in front of him on a table, we assume a huge table, like maybe as big as the world or something, a description of that algorithm, that actual algorithm written out. John Searle gets a series of lights flashing, which are the representation of that question after it enters the system. So there's a series of lights flashing. He then looks up in the algorithm what you're supposed to do when that series of light flashes, and then he carries out all the operations, and he runs through it all, and so on and so forth. And when he's finished, he types out something which he's executed the algorithm, in other words. Suppose he executes the algorithm, and then he types out an answer, and by assumption, this fools the observer. But he argues no understanding has gone on, because he doesn't understand Chinese. The answer's been given, but no understanding has gone on. Okay, ever since then, there's been a debate with hundreds of papers, several books, volumes of behavioral and brain sciences, in which people try to respond. This is supposed to show that that execution of an algorithm, he wants to destroy the whole computational theory of mind, like what Bach is talking about and AI and so on. He says no algorithm can ever carry out a mental action. Okay, so to identify the mental with the computational is just flat wrong. Turing test or no Turing test. And here's the proof. The proof is if John Searle were able to carry out this algorithm, and it did whatever you like, still obviously no understanding went on. So therefore, that shows that no algorithm can be a representation of a mental process. The whole computational theory of mind is therefore wrong. The computer model of the mind. Well, the answers generally are of the type that say, well, that he's overlooked the question of speed. It would take him forever to run through the algorithm, and the machine will do it instantaneously. So he comes back and says, okay, suppose you had the whole population of India inside the machine, and none of them understand Chinese, and they're all racing around like maniacs, doing pieces of the algorithm. And then somebody else comes back and says, Well, the point is that maybe he doesn't understand Chinese, but he plus the room understands Chinese, and then he comes back with an answer about that, and so it goes, up till today. Well, I'll leave you with that question and come back to it tomorrow. But those are the kinds of questions you very quickly get into when you make the non-naturalistic move that abstracts in principle away from biology. In fact, you get even stranger results than this. I'll bring them up tomorrow.
We have a 10 or 15 minute discussion if you like.
I just
And I was wondering if the intention with the T, because there's intent, causes a problem.
in a sense. I was thinking in terms of what's it called?
The question of technology, where is artifact and where is art?
And where is the line between them? In other words, is the creativity of language not just to say
New utterance that hasn't been said before.
Okay.
in the question of technology, I was wondering if the distinction, maybe an invisible line or a dotted line between art and artifact, changes how we have to look at the creative aspect of language, in the sense that not just a new utterance can be art, but an old utterance can be art as well as artifact. Just to change from the end of the discussion back to the beginning.
Well, the term creative aspect of human language is just, it's just an invented term, has no meaning other than what was given to it. And it was just a reference to a certain collection of properties of language. Maybe that's not a good term, so pick some other one. The Cartesians picked out certain properties of language, unboundedness, undetermination, appropriateness, and so on. I just gave it that name. Notice that creative aspect of language use has no aesthetic character. Like, it's not what we would call creative work. It's like saying some comment about a sports game to somebody you meet at a bus stop. That would be the creative aspect of language. It's completely mundane, ordinary, uninteresting, normal use of language. There's another form of creativity, something which has value as well. And in fact, if you go back to the tradition, actually to the Spanish philosophers, I think started all of this out back in, I think, the 15th or 16th century. Juan Quarte, who actually developed a lot of this before Descartes, he makes a distinction between three levels of, I forget what he calls them, mental action or something. Kind of one of them, I forget, is kind of like rote. Another is what I call the creative aspect of language use. The third is true creativity, which he, in sort of Platonic style, describes as a form of madness, like Plato thought about art. And it's the third type that would be real creativity. It's the second type, Quarte's second type that I'm talking about. The type that has these properties, but may have no aesthetic value. As to the distinction between art and artifact, that's a very hard one to make. Extremely hard. In fact, there's some interesting questions in art history about this. Questions that have a kind of a ideological content. It's now starting to come out from women's studies, in fact. A number of people have pointed out that objects of aesthetic value in most cultures throughout almost all of history have been created by women, but they're not considered art, namely textiles. For thousands of years, almost all aesthetic creation was textiles, and that was women's work. So that's considered craft, not art. It doesn't start being called art or entering into art history until men start doing it. The description is correct, in fact, and it raises obvious questions.
A question concerning your argument against computational theories, mind of that kind.
Yeah, I haven't really been arguing.
Well, if biology is what counts, what matters to have a mind, what do you say about different biologies? For instance, human biology and biology of people of different
Universe.
Yes.
So some invented universe.
Different biologies, different minds?
Well, I haven't given an argument, but let me make clear, what I've been doing so far is just to point out that computational theory of mind is intrinsically non-naturalistic.
Yes.
And it leads to questions like, how do we empirically defend the claim that machine is thinking, and so on and so forth. I haven't given my own criticism of this bit. My own criticism is going to be the same one as always. I don't think it makes any sense to depart from naturalism. And I don't think it makes any sense to ask about the biology of creatures that aren't in the universe. I don't think that makes any sense. Any more than it makes sense to ask about the electrical properties of aspects of invented matter that aren't part of the material character of the universe. I just don't think it makes any sense. Now, I can imagine ways in which it would make sense. It might make sense through the normal kind of abstraction that goes on in the sciences. Like, for example, mass points don't exist in the universe. Nevertheless, it makes perfect sense to study the behavior of mass points under Newton's laws. A form of mathematics which is perfectly well worth pursuing because it meets this criterion. It tells you something about the actual world. But if somebody were to create entities that don't exist, like mass points, and create laws that don't exist, other laws than the laws of this universe, and study what happens in that invented universe under those laws, and ask whether something in that universe is electricity, that would be meaningless. That's why nobody does it. And it seems to me it's equally meaningless in the case of psychology. And I think making this first funny step is already carrying you into meaninglessness. I tried to give an example. I mean, abstract biology of the kind that I described will, in fact, lead to apparent problems. So suppose, let me restate it. Suppose somebody comes along and does abstract biology, which abstracts in principle from biochemistry, the way psychology is supposed to abstract in principle from biology. Okay? So we now say, all right, we consider a bunch of primitive processes which aren't cells or ingredients of cells, but would have some of their properties. And we think of them as mathematical objects. We set up some criterion, whatever it may be, like being larger after a certain time than you were at the beginning, okay, which is a property of organisms. They're larger at a certain time than they were at the beginning. And then we consider the class of all objects, including organisms, the analog to this, which satisfy those properties. And we take something in this class outside the organic world, like some entity made up of non-existing elements, but getting larger as it... in fact, there are computer programs. Let me give you a real case. There have been studies of computer programs of growth. For example, carp are an interesting case because they apparently grow for infinitely. They seem to die only, there's like a random event that will make them die. But if you look at the distribution of carp in a big lake, their distribution, the weight distribution, can be predicted pretty closely on the assumption that they grow infinitely and a random event strikes them down every once in a while. That gives you a pretty good model. So people have therefore studied carp growth by computer programs, just making the fish, don't grow very well, but making the fish a little bit bigger each time in a computer model. And then saying, okay, that's a model of carp growth, and we get a model of carp distribution by throwing in a random event which knocks some of them out every once in a while. So we get a model for the carp in a lake. All right, so that meets these conditions. Okay, we picked certain processors, in this case they're Turing machine processors because we're modeling it in a computer. We picked their performance criterion, namely getting a little bigger and looking kind of like a carp, and being shot down by a random event every once in a while. And then we get we have the class of things that have that property, including carp and including these computer algorithms, and we're interested in all of them. Now, of course, this is done seriously. It's done in order to teach you something about growth. But suppose it was abstraction in principle. Then we would have funny questions, like, do these carp grow? The ones in the computer program. Do the things in the computer program grow? Well, I suppose somebody asked what Hoagland asks. How could I empirically defend the claim that a given model of a carp is growing, really growing? Now, I think that's a stupid question. It's not an empirical claim that these things grow. Since it's not an empirical claim, there's nothing to defend. Let me give an analogy. Suppose in 1900, say beginning of the century, somebody raised the question, maybe we can construct artifacts that'll do something like an eagle. They'll go up and stay up for a while and then come down. We'll call them airplanes. How could we empirically defend the claim that one of these things is really flying? Well, that would be an idiotic question. That thing is flying if you decide to call it flying. It's not flying if you decide not to call it flying. Doesn't matter what criterion it satisfies. It could fool you into thinking it's an eagle. It could be structurally like eagles. It could be whatever it's like. There is no empirical claim that the thing is flying. In fact, languages have decided to handle the question differently. Some have taken the metaphor fly and extended it to these things. Some haven't. So in some languages you say it's sort of gliding or something like that. But there was no right or wrong about it. It's just a question of how much to be impressed by a certain metaphor. Or take say high jumping. The thing they do at the Olympics when you try to see how high you can jump. Okay. Suppose that before anybody invented that crazy sport, somebody suggested that people who are high jumping are really flying, and then came along and said, how could we empirically defend the claim that they're flying? Okay. Well, it's stupid. It's not an empirical claim. I mean, you can call that stuff flying if you like. You cannot call it flying if you like. It happens, I was told once when I talked about this in class, that in Japanese it's called flying. Okay, in English it's called jumping. But is there any empirical issue at stake? I mean, there's no empirical issue. It's just a question of how to extend a metaphor. Similarly, to ask whether the carp are growing is a question of how to extend a metaphor. Suppose we say in English, I don't know what you say in Spanish, but in English you say that a submarine sets sail. You don't say a submarine swims. Okay, so set sail. Everyone know what I mean? Somebody translate it. No, that's not navigate. It's like a sailboat. When you have a sailboat and you get going, you put the sail up, and then the sailboat goes. That's called setting sail. Okay, setting the sail is raising the sail. Okay, so if you have a sailboat, okay, you have a sailboat and you pick the sail up, and the wind starts blowing. Picking the sail up is setting the sail. Well, in English, so it's not the general thing. Okay, as long as everybody understands. In English, I don't know what in other languages, you say that a submarine sets sail when it leaves New York for London underwater. Well, suppose somebody asks, how can I empirically defend the claim that the submarine sets sail? Right? And say, well, if it sort of looks like, in some respect, like a sailboat, and we pick up the respect. It's meaningless. Suppose somebody else were to say, look, I really think the submarine's swimming, like a fish. How can I empirically defend the claim that it's swimming? Well, again, it's stupid. In fact, all of these questions are stupid. And the reason they're stupid is because you've departed from naturalism. Once you've departed from naturalism, you have an algorithm for constructing stupid questions. Okay? And it's clear why they're stupid when we move to other domains. But the argument that I will give, I'll just repeat tomorrow what I'm saying now. I haven't given an argument, but the argument that I'll give is all these questions about the computational theory of mind are like asking whether a submarine is setting sail.
Sorry, but in that case, do you say that it's stupid, it's a really stupid question, but not because you're departing probably from naturalism, but because you're asking how it can be called. You are not talking about the thing, but about how the thing can be called. And that thing can be called so many ways that it's
that's
stupid.
The departure from naturalism.
Well,
you see, once we've defined the mental as the computational, we are just asking how a thing can be called. Notice the crucial difference between the 17th, 18th century post-Newtonian version and the computational science of the mind version. The Lametrie Priestley version, which I discussed earlier, post-Newtonian version, said thought is a property of matter, organized matter, just as attraction and repulsion are, electricity and so on. All right, that's naturalistic. Doesn't give any answers, but it sets a problem. This does something, this approach, the computational theory of mind, the one I just quoted from Ned Block's article, and the one that dominates strong AI and the rest, that doesn't give us a naturalistic topic, and in principle doesn't, because we're divorcing ourselves from the biological. What it does is ask whether we should call something thinking. Well, that's like asking whether we should call something setting sail or flying.
No, I completely agree with you. But I think that the Turing test has, besides that, a lot of other problems. I mean, even if you take it as these other people take it, because the problem in that test is not just the machine, because it's also the judge. I mean, in order that the machine can fool the judge, it's important the knowledge of the judge. For instance, it's important that the judge knows that he's doing with two persons or with the possibility that they're a machine. On the contrary, the answers he gets, he can interpret them as a stupid human being and not as a machine.
I agree that that's a problem, but I don't think it's the problem.
No.
Because that problem,
it is not the problem.
That problem could be fixed up. That problem could be fixed up by sharpening the test or something. The problem is thinking that it matters.
No, of course.
No matter
that's
how
the hard problem. But my idea was that if the test should be useful to decide whether a machine thinks as a person, couldn't it be useful to decide out of a judge that the person is a machine? That the person reacts as a machine?
Well, you're already...
Do you see what
I see what you're saying, but it seems to me you've already crossed into a world where we shouldn't be. You've crossed into the world of thinking that the questions raised by the philosophers make sense. Okay, if we were to agree that it makes sense to ask how we could empirically defend the claim that a machine is playing chess, then these questions would arise.
Okay.
But I don't think we should cross that border, because there's no empirical claim.
No.
It is just a question of how to extend the metaphor. See, and I think that Turing was getting at that when he said the question whether machines think may be too meaningless to pose, but educated usage may change so that 50 years from now will be meaningful. All right, let's apply that to flying. In 1900, somebody could have come along and said, the question whether airplanes fly may be too meaningless to pose, but I think that educated usage will change in 50 years so that people will call this flying. Well, okay, they happen to be right about English, wrong about other language.
No.
But there was no issue at stake. And moving on to questions like how could we empirically defend the claim or any of this other stuff is just often to...
Quite. I wasn't defending that that's an empirical question which can be decided empirically. On the contrary, I was aiming at this. Since this is a stipulation, you cannot just decide that the machine decide that you call thinking what a machine does, but you can decide that what a person does, that someone who is a person is a non-person. It's a political decision.
The Turing test.
Yeah, of course. Don't you think so?
Well,
I mean,
yeah, sure.
the judge.
If the judge confuses, you're right.
Of course.
Part of the logic of the Turing test is that if the judge, but of course Turing and the AI community and the philosophers who are involved in this stuff wouldn't object to that, because for them, thinking, having mental properties, which is being a person basically, just is carrying out certain software. That's intrinsic to the computer model of the mind. The computer model of the mind, which, well, let me repeat what Bloch says. He says, if we manage to construct automata in our computational image, that means we construct that class K, meeting the right kind of criteria, then we will naturally feel that the most compelling theory of the mind, hence the most notice that includes everything about persons as distinct from rock, bees or something, we will naturally feel that the most compelling theory of the mind is one that is general enough to apply both to them and us. So the result that you're pointing to, namely that people will be identified with machines, is exactly the result he wants, because the more compelling theory will be one that includes both them and us.
Yeah, quite.
So yeah, that's true, and that does follow from a non-naturalistic approach. Just as somebody might claim, taking the same approach, that the most naturalistic theory of the most compelling theory of growth is the one that includes that computer model of carp as well as carp.
A last question, perhaps? Well, then we'll see you tomorrow. Thank you.